Hello everyone, my name is Sugang Li. For those of you who doesn't know me, it's not. I closely work with Yan-Yong and Ray, and my topic is about future IoT network architectures and application in mobile sensing. So, Internet of Things is the networking of physical device, objects, and services that comes with a minimum connectivity capabilities. And according to a report by Cisco, by 2020, the number of connected devices will reach 15 billion. Such a huge number of connected devices not only bring us a lot of opportunities, but also impose many challenges to the current systems and the network infrastructures. In the aspect including security, connectivity, computing, and sensing. So let's take a brief look at these challenges one by one. In the IoT, security has become a serious concern for many years, as the hackers can possibly access all physical data in our life with the help of widely deployed sensors. The security challenges may lie in several aspects, such as the network protocols, the ID management, and privacy, and so on. Industry and researchers has come up with all kinds of solutions to address this concern. Besides the lighter weight security services for the network protocols, such as the 15.4 map security services, a bunch of privacy-preserving data mining techniques such as differential privacy are also proposed. In the connectivity perspective, there is always a strike for better radio connection, as we want to connect the more device in longer distance with lower power consumptions. And as a result, various low-power wireless transmission technology has been proposed. For example, like the Mf Iot, LoRa, and Zigbee. And the network communication has been shifted from a centralized client to server centralized manners to a more distributed weight. As the legacy architecture is not going to support the billions of connected devices. And the distributed protocols such as NDN, MQTT, and CoAP are proposed to establish direct connections between the devices and services. A large number of devices also means a large volume of data. All of this physical world data make people rethink the existing AI models to adopt these new data types in order to understand and predict the physical world more extensively. And for example, researchers have been using the crowdsourcing data to understand the noise distribution in the cities and use the roadside sensors to provide more fine-grained traffic controls. A large portion of this data are real-time data streams, and this drives the computing platform to support more timely data processing. Many real-time processing platforms are introduced, including the Apache Storm, Samoa, and so on. And most of this data are originally unstructured, which calls for the techniques for data federation, aggregation, and annotations. And last, in the perspective of sensing, researcher has been doing a lot of work in the sensing modalities, energy consumption, low energy consumption platform, and form factors. In the sensing modality part, researcher comes up with a lot of works on the compressive sensing, collaborative sensing, and mobile sensing. And for the low power consumption platform, there are also many solutions has been proposed, such as the transmit only, RIO, Telos, and so on. And for the form factor of the sensing part, the device form can vary from a very heavy loaded LiDAR devices to a battery-free RFIDs. So, in this dissertation, we are trying to answer the questions in the following scopes, including the connectivity, computing, and sensing. So in the connectivity part, we are seeking a network architectures to interconnect the isolated domain without bothering the complicated network address translation service And meanwhile, we would like to enable the service-oriented communications with such architectures. And in the computing part, we propose a new data aggregation solutions to reduce the network traffic caused by the high volume of small packets that generated by huge number of IoT devices, which will further introduce tremendous overhead to the networks and the server. And finally, we're going to introduce a real-time mobile sensing techniques which can leverage general purpose sensors for special tasks. And here is the overview of my dissertation. In the first part, I'm going to introduce mobility first, architecture with global reachability and communication diversity. And the second part, I will going to introduce our IoT data aggregation works. And in the third part, I'm going to introduce sensing techniques that are used to sense the approaching car for the pedestrian in real time. Let's take a look at Mf Iot. So as I just mentioned earlier, the number of connected devices is growing dramatically. Cisco report the number of connected devices can reach 15 billion by 2020. By the connected device, we usually means a device that come with some minimum level stack. If we extend the idea of connected device to things such as RFID, objects with just QR code, and the number could become trillions. It is really challenging to configure and manage them by human in a centralized manner. As a result, the things has to be self-manageable in a distributed way. And in other words, there should be no obstacle to establish direct thing-to-thing communication. So we consider a future in IoT architectures need to support global reachability, where things can reach each other with minimum overhead. And second, things have become mobile, such as UAVs, robots, sensors on the vehicles, which can move across different attach points and domains. And we envision an IoT architecture should also provide mobility support. Like other internet devices, a future IoT architecture should allow things to have rich communication patterns besides the data collections. D2D, multicast, anycast are highly desired. For example, an actuator may need to multicast data request to a group of sensors in order to make an action. So at the same time, such IoT architecture should support the communication between the device with different capacities. Low power sensors, mobile phone, and data server, they should be able to talk to each other without complicated configurations or proxy functions. And finally, we envision that such architecture should enable service-oriented communication, which allow the user to address services instead of devices. So essentially, what we really care is the service or the data that provided by those devices instead of the device themselves. So let's take a look at the state of the art. So in the IP network, in order to address the shortage of IP address, network address translation service is widely deployed, and the local things address are hidden behind net. And it's cumbersome to establish direct communication between the local things and remote data consumers. And moreover, if the things moves, usually the private address has to be reassigned and the session will discontinue. There are many name-based solutions such as NDN, or joins, or co-app are proposed to address part of these issues. However, some of them may have redundant application functionalities, and they don't have efficient support for the rich communication patterns, and they don't come with a native mobility support. That's why we call for a new architecture for the future IoT. So we would like to introduce mobility first here. So in mobility first, essentially we are using a global unique ID, a GUID, to name all the devices and services and application in the networks. GUID it's a persistent ID, and it can provide you with self-certifying public keys. And in order to make that happen, in the core of the mobility first networks, we have global name resolution services which is provide you with the service to store the mapping between the GUID to their locators. And in order to support the seamless handover, we also introduced the lane binding features in the mobility first, which can allow us to support the smooth handover. So here is the overview of Mf Iot. In Mf Iot, we maintain the GUID-based communications that are provided by mobility first, which means no matter on the sensor node or on the infrastructure nodes, both of them are using the full-length GUID to communicate with each other, and we enhance the efficiency by introducing the local unique ID. We compress the long GUID to a shorter version in a resource-constrained network, so that in those networks they can use a shorter version of the ID to forward data and route data, because they have a very limited size of MTU. And we also enable the service-based communication in Mf Iot, which means we can support the service migration and service caching. So first, let's take a look at the components in Mf Iot. So in Mf Iot, we have two domains: the core networks, which we have the GNRS, and we have infrastructure nodes, which includes the MF clients and MF routers. And in the Mf Iot domains, we have two components. The first one is the IoT nodes, which can provide you with the forwarding service, and you can run applications. And in the gateway side, it can also provide you with the forwarding service and also the gateway service. So let's first take a look at how this name translations between a local unique ID to a global unique ID can happen transparently within Mf Iots. I would like to give you very concrete examples. So in the first examples, let's say we have two nodes trying to talk to each other, like N1 and N2. The first thing, the only information that N1 needs to know is the GUID of N2. Then he can go to the gateway to retrieve the area ID of N2, and then use the area ID of N2 to send the message directly. And the case becomes more trickier if we need to establish a connection between a local IoT node N1 and an outside node N3, because we only have a limited size of the area ID, so we are going to introduce a type to differentiate the local area ID from the remote area ID, so that we can periodically recycle the area ID for any remote node, so that we can utilize a very limited size of area ID to name as many as possible outside node. And we also support the service-based communications in Mf Iots. So we support the service migration, which means multiple devices can provide the same service if they claim they're using the same service GUID. Like in the first example, both N1 and N2 can provide service S1. Imagine that you have a house that N1 is a temperature sensors, and N2 it's a smart thermostat that comes with temperature sensors. And once your N1's battery is dead, and it can migrate its service to N2, so that whenever a consumer's N3 trying to pull the data from S1, the entire process will be agnostic to N3, and the packet will directly forward to N2, because N2 is now hosting service S1. And we also support service cachings. So like the example in the right-hand side, we have three nodes, N1, N2, and N3s, and N1 and N3 that hosting the temperature sensing and the light sensing, and they can ask N2 to cache the data for them, so that they can go into a sleep mode. With this capability, essentially we can introduce a smarter duty cycling scheduling algorithms, so that we can maximize the local IoT domain's battery lives. And we also treat all the network functionality as services, including the forwarding service and gateway service. We are using the LUID to name all of these services. And finally, we support the rich communication patterns, which means we can enable the communications between heterogeneous devices, including the IoT to IoT communication, IoT to infrastructure node communication, infrastructure to IoT communications. And we unify the unicast and multicast by introducing the same type of GUID, which means as long as the only things that the application need to know is they need to know the destination GUID, and the network will handle the unicast or multicast logic for the applications. We evaluate our Mf Iot over a large-scale simulation that has up to 400 nodes. Here is the data trace distribution that we use to run the simulations. So in order to compare, we also implement two other protocols. The first one is 6LoWPAN, IPv6 for low power personal area networks. And the other one is end-to-end query response. And we evaluate their performance in terms of the average latencies and aggregated traffic, network traffics. As you can see here in the plot, our Mf Iot outperform the other two algorithms because in NDN, their protocol is a query response protocol. They need to pull the data every 2 seconds, which will introduce very long latencies, and a lot of traffic is wasted for the pooling. And for 6LoWPAN, so every packet goes through it because they force the network to form a tree topology. So every packet has to go through the gateway, and which will introduce a high latency, and the network get easily congested when the traffic reaches to a certain threshold. And for our Mf Iot cases, our Mf Iot multicast is slightly better than the Mf unicast is because we are leverage the broadcast media on the sensor nodes, which can further save some traffic. Here we also conduct a behavior study to understand the mobility performance of our Mf Iots. We have two scenarios. The first scenario is IoT to infrastructure communication scenarios. So the x-axis is the time, and the y-axis is the delay. As you can see here, at the beginning, we will introduce a spike for the initializations, and after a very short time interval, it will become stable. And at 12 seconds, the infrastructure node moves from one domain to another domain. So, and then we will see another spike because of the GNRS lookup, and the lay binding is happening. And after 5 seconds, it will become direct transmission because the name to locator mapping has been updated in the GNRS as well as the source access point router. So you can observe the similar behaviors that in the second scenario where we have IoT to IoT nodes communications. So in both cases, we are only going to experience a very short time interval after if there is a mobility happens, which means our Mf Iot can support the mobility and recover the networks in a very short times. We prototype our Mf Iot on the real sensor board. So we are using same R21 boards, and we are implementing Mf Iot protocol stack on the RIO operating systems. And I will show you guys a real demo to show the feasibility of Mf Iots. So this demo is essentially end-to-end demos that combines with all the components in Mf Iot as well as the mobility first. So the story of the demo is actually pretty simple. That imagine that you have a house that I guess most of the graduate students have to imagine. So you can install a bunch of the motion detectors, and so that if someone triggered your motion detectors, the motion detector will send a notification all the way through the Mf Iot networks and as well as the mobility first network to your civilian cameras. And your civilian cameras were going to send another notification to your client to notify whether you want to take a look at the video or not. And your client would just begin to pull the real-time video stream from the civilian camera. So the first scenario is the basic one that is exactly the same as that. The message flow is exactly the same as I just described. So I step in, I trigger the sensors, and video is playing on both of the laptops by MF Multicast. Okay, yeah, that's it. So the second case is more interesting because we are really testing the mobility support for Mf Iot and mobility first. So essentially the overall demo story is the same. The only difference is that we are emulating the handover by unplug the client from one access point and we plug it to another access point. We do this because that in such a short distance, it's very difficult to do it wirelessly. You can see, step in, trigger the sensor, and the video is playing. Then I unplug it, it stops, and plug it back. And the video will just play from the point that I unplugged from the access point, which means none of the video frame get drops. The first scenario is similar to the previous one. Due to the time limit, I'm not going to show you. So to recap this works. So in this work, we study the requirements in the future IoT architectures, which calls for the global reachability, mobility, which communication pattern, and it should be friendly to resource-constrained devices. And based upon the study, we propose Mf Iot which we extend the mobility-first networks into the IoT world, and we're still using the GUID-based communications, and we support which communication patterns, and we are enable the service-oriented communication. And we study the feasibility and efficiency of Mf Iot through detailed simulations as well as the demos. And here is the publication that related to this project, and our demo won the Best Demo Award at CPS Week 2017. So next, let's take a look at the next project, which is about aggregating the IoT traffic by using the edge clouds. As I mentioned earlier, a huge number of IoT devices means introduce a huge number of small packets into the networks. And I have a data to show that the connected IoT device, it's like 23 billions for 2018, and you will reach 75 billions by 2025. And I also found another study that report that 75% of the IoT sessions transfer less than 1 KB data. You can see in these tables, they are categorized their IoT application into 5 types, and for the average packet size, none of them is bigger than the 700 bytes. So this new network traffic patterns introduce a lot of overhead for both the networks and the receiving service, because every packet requires a routing table lookups, and it will generate a packet. It will generate interrupts at the server side. And one way to tackle down this problem is through the aggregation, and which means we can aggregate the packets in the network so that in order to reduce the overall network traffic. But there are few works has been done in the core network because of the resource isolation technology are not there. Usually that requires the effort from multiple parties that includes the network service providers, the computing service provider, and the application providers. But now, since we have the resource isolations, an application provider may have owned both the virtualized computing resources like the VMs and mobile edge clouds or containers, as well as the virtualized network resource. So it can do the optimization all on its own. Even though the technologies are there, so there are still many challenges for such in-network aggregations, because there is always a trade-off between how many allocated computing resource versus the reduced traffic. So for example, like given a fixed number of aggregation nodes that we can place in the networks, where to place them and how to place them in order to minimize the overall network traffic. And second, given a fixed number of traffic hotspots, how can we find those traffic hotspots? And how can we place the aggregation node into those traffic hotspots in order to minimize the overall network traffic? And third, in order to support the in-network aggregations, how can we filter the packet, the aggregated packet from the normal traffic, and as well as how can we steer the traffic towards those aggregation points? So there are many existing works there. In the wireless sensor network area, people do this data aggregation service, research based because they want to save energy as much as possible. And in the core networks, there are also some works have been done to reduce the overhead, but they are more on micro levels on the routers and on the servers. So our contribution of this work is that we model the IoT aggregated traffic for any general networks, and we minimize the traffic by introducing two heuristic algorithms, and we also design an efficient routing and packet handling scheme that based upon one of the future internet architecture mobility first. So I would like to introduce a general model, a general system model that can be easily implemented on any network architectures. In this model, we're going to have four components. There are the computing routers, the application-specific controllers, and the source nodes, and the destination nodes. So for the computing router, it can switch between two roles. Either it could be a routers, and it could be a router plus the computing nodes, aggregation nodes. And for the application-specific routing controller, it's essentially a centralized controller which can help us to sample the edge network statistics and compute the routes for each aggregated flows. And of course, we have a source node that can generate the data and the destinations to consume the data. Here, I would like to also give a brief definition of the aggregation here. What we mean by aggregation is really mean that we can collect raw data packets for time t and send a constant number of aggregated packet out. And the example aggregation operation could be the minimum of aggregated data and the maximum of the aggregated data, and the average, and the deduplications, and concatenate. So here I would like to start with simple topology to describe our models. So I would like to start with this bars and star topology. So in this topology, all the computing nodes, they are aligned on a straight line. So that's why we call it a bus. And then we can attach the sensor node or the source node to each of the computing node to form a star. So that's why we call it a bars and star topology. And its cost function, the cost function means the total network traffic can be expressed in this way. It may seem to be a little bit complicated, but it's actually not that difficult to understand. So there are three components. The first component, 1 over t times d, it's the aggregated traffic. Because we say that we will aggregate the traffic for a time t. So essentially the data rate on that length will be 1 over t. And we times the hop counts between the last aggregation points to the destinations. And the second component is the sum of costs from the source node to their first aggregators. So that's the second component. And the third component is the sum of costs for those traffic that has never been aggregated and directly sent to the destinations. And for this topology, we can have two closed form for the boundary cases. In the case 1, no computing nodes, it's aggregation node. So we can express it in this way. And in the case 2, all computing nodes are aggregation nodes. We can also find a closed form for that. So next, I'm going to extend my topology to a more general networks, which means all the computing routers can interconnect with each other in a mesh topology. They can connect with each other as many ways as they want. So for the cost function, we will still have a similar form as the previous models. So we'll have the first component is the aggregated traffic. The second component is the traffic that from the source node to their first aggregator. And the third one is the traffic that has never been aggregated and directly sent to the destination. And again, we have closed form for these two boundary cases when there's no computing node, it's aggregation nodes, and when all the computing nodes are aggregation nodes. Since the boundary cases has their closed form, the really tricky part is the case in between, right? Where there are some nodes are aggregation nodes, some nodes are not aggregation nodes. Here, I would like to propose a theorem that is the problem of finding k aggregation node in such network in order to minimize the sum of the cost is actually an NP-hop problem. Because we can reduce a very well-known NP-hop problem, which is the minimum sum of square clustering problem, to our problems. And in fact, if you take a deeper look into these cost functions, when the t at the aggregation time window, it's much larger than the packet sending interval, which is normally the case, right? The first term, it's negligible because it's 1 over t. And because the number of the source node that directly connected to the destination it's also limited. So the third term, it's negligible. So our objective to minimize for the optimization is to minimize the sum of the cost from the source node to their first aggregation node, which is this second term. So here we would like to introduce two heuristics. The first heuristic is, we call it a provider-defined placement scheme, k-agnos, which means the application provider can specify the number of aggregation nodes they can place in the networks. The algorithm is somehow sort of similar to k-means algorithms. We start with placing k aggregation nodes in the networks randomly, and then we assign the source node to their nearest aggregation nodes. And then we iterate between two steps. In the first step, we search a non-aggregation node that can lower the cost. And in the second step, we reassign the source node to the new set of aggregation node. And then we will stop the iteration until the cost is stable. So here I would like to show two preliminary results. Like for the virtualization purpose, I'm using a grid topology, and I attach an equal number of source node, like those little blue dots, to the to the computing nodes. Yeah. And then in the first case, when k is equal to 1, the ideal case is the location of this aggregation node should be at the center of the grid topology, because that's where all the sum of the cost is minimum. And our algorithm can help us to find this location and place the aggregation nodes there. And when the case, when k equals to 4, the ideal case should be that all four nodes should be distributed uniformly in this grid topologies, and and the result shows that our algorithm can again help us to find the locations and assign the source node to those aggregation nodes.
Can I ask a question?
Yeah, sure.
That's assuming that the costs are all linear. You can imagine latency costs being unlinear, being nonlinear. If the latency is over a certain amount, the car is going to crash, so you don't... if the cost is nonlinear, you might give up some connectivity completely in order to have the other ones inside?
Right, so the cost is assuming, is defined by the traffic. It's not defined by the latency. So if it's a latency, but essentially the cost could be just a distance matrix that applied into this case. And I believe the k node should work in...
You think it's always linear?
Yeah. Oh, sorry. Yanni is down. Let me reconnect. Oh, Yanni, can you hear me? Can you hear me, Yanni? Oh, okay. So we can conclude that the k-node algorithm can perfectly allocate the aggregation node so that the objective cost function is minimum in simple cases. The second heuristic is proposed to handle a more challenging task where the number of aggregation nodes is determined by the number of traffic hotspots. So it's more trickier because we don't know the number of traffic hotspots beforehand. The algorithm itself needs to be figured out how many traffic hotspots are in the network during the iterations. Unlike the previous algorithm where we can set k nodes in the networks, this time we will consider, at the initial stage, we will consider all the computing nodes are the candidate aggregation nodes. Then we start to shift these computing nodes and merge them according to some metrics. So, and there is only one parameter, which is the radius r, which defines the range of the associations. So in this case, this one is the computing nodes, and we can find the r, and we associate all the source node that within this range to that computing nodes. Okay, so at each step, we will compute the cost of this node that's shifting to all of these neighbors, and we will determine the shift vectors by choosing the smallest one. And so it's worth it to mention that we should be very careful about the merging order, as the shifting vector for all the nodes are generated simultaneously, like this graph. So this graph is essentially because like C7 is the center of this grid. So this tree topology is formed by the shift vectors that generated all by all nodes. And if we merge C9 first to C2, then C5, C6, and C3, we find out C9 is not available to be merged anymore. So we introduce a topological sorting to guarantee the merging order is happening from the leaf node all the way to the root node. And We also have two preliminary results, one with one traffic density, traffic hotspot, and one with two traffic hotspots. And in both cases, our aggregation agnode shift can allocate the center of the traffic, to allocate the place of the traffic hotspots, which means we can use it to estimate how many aggregation nodes that we need to place in order to cover all the traffic hotspots in the network. And it is also possible that at the load at the traffic hotspot exceed the capacity of the aggregation nodes. So we further introduced two load with distribution algorithms to redistribute the load for that aggregation node. And the first one is called share with neighbors, which means is that you can share its load to its neighbors in a round robin fashions. And the second one is called it's K agnodes, which is the same as the previous K agnode algorithm. The only difference is that this time we are running the K agnode algorithm in a subset of the computing node to redistribute the load.
So you're assuming that you can change these parameters in the network fast compared to the measurement time. So that this is essentially simultaneous changes you can make.
Right.
But these nodes could be very far apart in space.
Right. So we are assuming there is a centralized controllers that can sample the statistics on all those links and the data rates, and so that can make a decision very quick.
But it's quick compared with the data, with the rate of change of data. For example, if a fire occurs in a building, all the little IoT sensors are going to start sending out their packets at once. So there'll be a spike in traffic.
Right.
And you're saying that you can change this network fast compared to those spikes.
Well, the speed of changing the network depends on how fast we're going to sample the networks. So if you are going to sample the network very fast, and of course they will give you additional overhead because each time you sample the network. Right. So that's the part that we don't really study in these works.
Okay.
Right.
Can you use in principle traffic patterns, historical traffic patterns?
Yeah, we can do that. So here, basically what we use is that we assume the traffic pattern is more stationary. It's not like change that dynamically. Yeah. So besides the algorithm-wise challenges, we mentioned that the system implementation is also very difficult for the current IP networks. So we're going to propose a system design over mobility first. So in this system design, we're still going to have an application-specific routing controller, which is a centralized controller that can help us to sense the data rate and hop counts. And you can run the heuristics to associate the source node to the aggregation nodes. And it can insert routes to the GNRS. So, and also we will have a computing router, which we are using SID, a service ID, to flag for each of the aggregated packets in order to differentiate the aggregated packet from the normal traffics. And we are introduced GUID index data handler so that we can create a handler pool so that each of the computing router can handle multiple aggregation flow at the same time without introducing additional ID logic. And we design an efficient routing mechanism over mobility first by introducing a two-level hash functions. So essentially that at each of the source node, the only thing that you need to know is the destination GUID. And each of the intermediate router, we're going to perform a hash function that combines with its own GUID with the destination GUID, and use that hash value to look up into the GNRS to find out where is the next aggregation point. So with this approach, essentially that we can simply use the mobility first and the GNRS to set up the entire aggregation path with minimum overhead. We evaluate our heuristics with some real data traces. So we interpolate San Francisco cap traces into 3,000 caps because we need to generate, we want to generate more data, and we take a snapshot at 3 p.m. every day for 10 days. And we also use the San Francisco access point data trace, like this one, to generate the Voronoi diagram in this one. And each of the cells will assign the caps to the access point if they are in the same cells. And we generate the traffic at each of the access point by Poisson distributions, where the lambda is determined by the number of attached caps. So first, we would like to evaluate the provider-defined placement schemes. So in order to compare, we also implement two baseline algorithms. On-path algorithm is essentially that we place the k aggregation nodes on the shortest path from the source node to the destination nodes. And we don't play it randomly because if we have a limited number of those aggregation nodes, if we play them all the way back to that close to the source node, they will be only effective for a limited number of source nodes. So we place them as close as possible to the root node. And the first assignment algorithm is that we randomly place k aggregation node into the networks, and we assign the source node to their nearest aggregation nodes. So in the first scenario, we vary the number of aggregation nodes that we can place in the networks, and you can see that our k-agno algorithm, the green line, outperform the other two algorithms. Even though it's so similar to the first assigned algorithms, it can still have some improvement because we have the optimization steps after we randomly assign the source node to the aggregation nodes. And in the second set of experiments, like the C, in plot C and D, we're going to see whether our cost function is sensitive to the aggregation time window. So we vary the time window from 0.1 seconds to 1.5 seconds. And as I just mentioned that if the time window is much larger than the packet sending intervals, and it should be insensitive. And the result here just confirmed that because you can see for all three schemes, the overall traffic remains the same. And of course, it will increasing the latency because each packet has to spend a longer time when it's waiting at the aggregation point. So which indicates that when we really want to choose aggregation time window for the systems, we choose a relatively small one because it doesn't affect the total traffic, but it will lower the overall latency. And last, we're going to see whether our k-agno algorithm can adopt to a more large-scale network. So we vary the network size from 10 by 10 to 20 by 20. And in all the cases, our k-agno algorithm outperformed the other two algorithms because we don't assume there's any specific topology or there's any specific constraint. So it's robust regardless the network scale. And next, we're going to see how does our algorithm perform in the network-defined placement scheme. So here, I would like to introduce a new metric, which is the efficiency per aggregation node. It can be defined as the normalized reduced traffic divided by the number of aggregation nodes that we place in the networks. So in order to compare, we are comparing the agno shift algorithm with k-agno algorithm when k is equal to 4 and k is equal to 8. And you can see here in all the cases, our agno shift algorithm outperform the other two schemes, especially when the trace ID is 3 and 6. It's much better than the other two because in these two cases, the number of traffic hotspot is much smaller than 4. So our agno shift algorithm can identify the correct number of the traffic hotspot in the networks, but the other two is sort of like constant number of hotspots. And next, we are going to further evaluate the low redistribution performance of those two algorithms, the share with neighbor and k-ag nodes. So here we also use a new metric to evaluate them. The physical meaning of this metric is the average of the normalized error. So essentially we vary the capacity threshold at each of the aggregation nodes, and you can see that in the first plot, share with neighbor is always better than k-ag nodes, because it's natures of the round robin, which can redistribute the load more uniformly. And in the second case, they almost overlap with each other. That's because when we take a deeper look into the result, we find that both algorithms, in this case, they are resulting in the same set or the similar set of aggregation nodes, which makes the result is really similar. So to recap this project, we model the aggregated traffic of general networks, and we introduce two heuristics algorithm, k-ag nodes and ag node shift, to minimize the total network traffic. And we design our system over one of the future internet architecture, mobility first, and eventually we evaluate the performance of our heuristic over real-world data traces. And the last part of my dissertation, it's about sensing techniques that used to detect the approaching car that using the embedded microphone in the smartphone. This sensing technique is more application driven. So there is a new German word called Zombie, which comes from the smartphone zombie, which means the people who are walking slowly and glue their eyes to the smartphone. And however, this becomes a new public safety hazard as the distracted pedestrian cause accidents. And according to a study in 2013 by from DOT, in the United States, a pedestrian was killed every 2 hours and got injury every 8 minutes. And from 2004 to 2010, the phone-related injuries increased from 559 to 1,506. I believe this number has further increased in the past few years because we are now all using smartphones, and it's more powerful and it's more entertaining. So in fact, people have come up with solution for this problem for a long time, and the solution can be categorized into two types. So in the infrastructure side, all kinds of this vision queue are being placed in the cities to remind both the drivers and the pedestrians. And however, this kind of solutions requires it's only available in some big city, in some certain area, and it requires the continuous support from the government. And the other type of its solution is relies on the technology, like from on the vehicle side and on the pedestrian side. On the vehicle side, like DSRC, it requires a special chipset on both the vehicle and the smartphone, which is not available pervasively. And also the LiDAR and camera are also available on some new car and some high trim models. So on the smartphone side, researchers has also come up with the solution that using the smartphone to sense the approaching car. Basically, they're using the smartphone's camera to detect if there is a car that's approaching the pedestrian or not. However, this requires smartphone has to be pointed to the coming vehicle, which is not the case in most of the scenarios, right? So here is the question. So can we actually use a very lightweight solutions that can sense the cars for the pedestrian without any specific holding positions? And the answer is yes. So we propose a sensing technique that use the off-the-shelf smartphone microphones, and we can sense the car from unspecific holding positions, and we can sense the car timely and accurately. And our sensing technique is robust against different car models and environments. So let's first take a look at why this problem is so challenging. hear anything? Yeah, never mind. So this is the audio that I'm taking when the pedestrian is sitting on the sidewalk and there is a test car that's driving towards the pedestrian. It's actually, when you really hear it, it's actually pretty quiet. So there you can see there's no instantaneous cues for the car's presence, and there's no outstanding acoustic features for this audio frames. So this is due to the nature of the car sound. So vehicle engineers spend decades to make the engine noise quieter and quieter. So especially when a car is running on a constant speed, the noise mainly comes from the tire and pavement friction noise. So compared to other acoustic signal in our daily life, such as the speech and the steps, this car sound does not have very outstanding acoustic formats, and the current techniques that used to detect the sound cannot be used in our case, such as Doppler shift, which requires us to observe a specific frequency components, and because we don't even know what is the frequency we should look at, so Doppler shift is not suitable here. And MFCC, which is mainly designed to capturing the characteristics of human voice, and we will show it later that is indeed worse than our solutions, even in a very controlled setup. So to address these challenges, we propose our system Auto++, a car sensing techniques that using the smartphones, and we can divide our system into 3 modules. Like in the first modules, we do the processing of the audio frames, which we transform the raw audio frame into spectrograms, and then we can further determine if there is a presence event in this short spectrogram. So as I mentioned earlier, observing an event when a car is present is a very challenging task because there is no outstanding features. So we take a further look into the signal, and blue axis is time, red axis is the frequency, and yellow axis is the magnitude. And we take 2 snapshots. One is taken when the car is far away from the pedestrian, one is taken when it's getting closer. And we put 2 snapshots into one plot, and if we set one power threshold here, and we can observe that when the car is getting closer to the users, the frequency, we can observe the frequency with higher components, the component with higher frequencies. So this is due to the path loss phenomenon. So for simplicities, we are using a free space path loss model to describe it. So which means the higher frequency component will suffer higher loss. And because this data point is the top right data point that we're looking into this FFT, so we call this feature called the top right frequency, which is the maximum frequency whose power reaches a certain threshold. And however, determining a fixed threshold is not actually a trivial job, because this threshold, power threshold, is going to be impacted by so many factors, such as the car types and environmental noise. And instead of setting a constant threshold, we are going to use a more smart algorithms. So we get some idea from the image processing area. So if we have an image and we want to extract the edges out of this image, we're not going to set a threshold to extract the edges. Instead, we're going to calculate the gradient of these pixels, and only select those pixels with high gradient values. So similarly, our spectrogram is nothing but a picture, right? So the top right frequency is the outline of this mountain. So we adopt the idea of the edge detection in the image processing field, and we first apply the Gaussian filtering to smooth out the pictures and then we calculate its gradients, and eventually we'll only keep the main edges in these pictures, which shows like this. And after we calculating the top right frequency trace, and we can further look at if there is a peak in the trace or not. So if there is a peak in the in these windows, and we say that okay, that's an empty window. If it's increasing in the window, then we say there is a car present. After we detect the car's presence, we can further determine the coming direction of this car. So most of the smartphone nowadays comes with two microphones, one on the top, one on the bottoms. So we can essentially estimate the TDOA, time difference of arrival, of these two channel signals, and by calculating their cross-correlation functions. And the lag with the maximum value is actually the TDOA value that we look for. Since we are using the raw audio data to perform these TDOA estimations, because they can give us very high sampling rates, can give us some very good time resolutions. But the raw audio signal is very sensitive to noise. As you can see here, when the car is far away from the pedestrians, the TDOA value is actually fluctuating across the zero line. But if we are using our presence detection as a trigger to start the direction detection, you can see that from this point, the TDOA value is much more stable. So our presence detection algorithm can use as a trigger here. And with such sensing techniques, we can enable several important applications, like besides the pedestrian safety alerts application. In the first case, we can also use that to to monitor the residential areas traffic where the navigation apps is not turned on that often, and we can also use that to enriching the augmented reality games. We can basically mark the moving object in the screen with a dot to remind the player that there is a car is coming. So we evaluate our sensing techniques through very comprehensive experiments. So our objective is to understand whether our car can detect the presence of car in time and with very high accuracies, and whether our direction detection algorithms can detect its direction correctly or not. And if we are using that as traffic monitoring apps, what is the counting errors? And we test with a wide range of test cars. So we have covered 7 models, which is most of the model that you can see on North America. We have an electric car, sedan, SUV, and sport car. So we also cover various environments, including the parking lot, residential area, campus road, and shopping center. So first, let's take a look at whether our sensing techniques can detect the approaching car in time or not. So in this experiment, we ask the user is standing on the sidewalk, this red dot, and the test driver drives our test car by following these blue arrows. And we also implement 2 algorithms to compare with our edge detection-based algorithms. The first one is using the raw audio signal. The second one is by setting a constant power threshold. As you can see here, our edge detection-based solutions outperform the other 2, and it can detect a car 5.7 seconds ahead. And even for electric cars, we can achieve the similar performance, which is like almost 6 seconds ahead. We can detect it.
How fast were the vehicles moving?
There is a speed limit on campus, so it's around 30 miles.
Okay.
Yeah. We like to drive fast, but police comes, so.
Sugang, we're about at 1 hour 15 minutes.
Oh, okay, almost done. It's going to wrap up. So also we evaluate the accuracy of our presence detection. In the quiet case, we can achieve 100% true positive rate and 0% false positive rate. And in the most challenging case, in the outdoor shopping centers, the true positive rate is 84% and false positive rate is 13%. And we compare our solution with the MFCC-based solutions. So even for the best case of MFCC-based solutions, it can only achieve 82% accuracy, which is much lower than 100% in the ideal setup. So, and we further evaluate our direction detection algorithms. There is the histogram of the detections. We can achieve, for 84 of the time, we can correctly detect its directions. And most of the incorrect detection happens when the car is far away from the users. So, which means if we can continuously monitor its coming directions, and we can increase the certainty of the prediction. And our detection is robust across all the noise environment. And finally, we are going to evaluate the errors when we are using it to count the vehicle on a suburban road. So in the most challenging case where the average car count per minute is more than 8, our counting error is less than 1 when the user is standing on the sidewalks. We implement our system over Android platforms. For the image processing part, we are using the native OpenCVs, and we profile the memory and CPU usage of this sensing service. And even in the peak usage, the CPU utilization is only 1.8% for a Nexus 6P, and the memory does not exceed the system pre-assigned memories, which indicates our sensing service has the potential to become a background service for Android devices. And to recap this project, we proposed a sensing system that used off-the-shelf smartphone and smartphone microphones, and we introduced a new feature and introduced a reliable edge detection-based algorithm to extract these features. And we conduct very comprehensive experiment to evaluate its performance. And we implement our system on Android platforms. And we publish these works on Ubicom 2017. If you take interest, I can forward you with the paper. To conclude my dissertation, so I have 3 parts. In the first part, the connectivity part, we studied the requirements for future internet IoT architectures, and we'll propose a new architectures which support the global reachability and mobility, and we develop an end-to-end demos of Mf Iot in realistic scenarios. And in the second part, which is the computing part, we model the aggregated IoT traffic in general networks, and we propose 2 heuristics to minimize the network traffic given different assumptions, and we design an efficient aggregation system over mobility first. And in the third part, we propose a vehicle sensing system that used off-the-shelf smartphone microphones, and we discover new features and that can catch the presence of the vehicles and a robust algorithm to extract these features, and we conduct a very comprehensive experiment to evaluate Auto++ performance. And here is the publication that I had during all my PhD times, so you can take a look. I'm free to take any questions.